Okay, we're reviewing topics that are important for Algebra 2, college algebra. And as we do that, we're going to take a look at square roots. Now, this idea has always perplexed me a little bit. The books will often talk about a principal square root. And here's the reason, of course. If you take a square root, it's what two numbers multiply themselves make 9. Well, it could be 3 times 3, right? So the square root of 9 could be 3. But it also could be negative 3 times negative 3. Don't those also make 9? And so it's been a little strange to me when they choose to go with only the positive root and when they choose to consider both, because we do quadratics and they want you to say plus or minus 3. And so it is a little bit confusing. Until we get further, we're going to just use the positive here until we get to some ideas that need it. And the reason they're doing this, the reason for the confusion is that it has to do with the idea of a function. And we'll go through this idea later. I'm not going to go all into it here, but the function can only work with the positive square root. And so I think that's why sometimes they selectively choose just the positive, and sometimes they want you to remember that it's plus or minus 3. And I think the reason is that they need to remember that the square root function can only work with the positive. So anyway, the point here, what they're saying is the principal root, for now, we're just going to work with the positive square root. Okay, so you know the idea of a square root. Some mathematicians said, hey, what number times itself could turn into this 100, for instance? And when they found that, they said, hey, instead of writing all this out, that 10 times 10 can turn into 100, they just created this shortcut idea. And so the square root of 100 is 10. 10 times itself makes 100. This is all just some mathematician's language for some shorthand. So the square root of 100 is 10. Now this one is very strange because we have a square root inside of a square root. And so I would first, it's like, please excuse my dear Aunt Sally, the innermost part of the house would need to be cleaned up first. So the square root of 16 is 4. Now we clean that up and we're still inside a square root. The square root of 4 is 2. Now again, we're working with principal roots here, even though technically a square root is a plus or a minus. But here we're going to limit ourselves to the principal roots. Okay, now see here, we've got a house that needs to be cleaned up. This is a grouping symbol, so we're going to add those together first, then take the square root and get 13. Now, we have two grouping symbols with a subtraction between it. We have to do the grouping symbols first. So this is 7 and 9, then it becomes negative 2. Okay, so the square root of 225, that is 15, isn't it? 15. Yeah, so that's 15. Now I have a root inside of a root, so I'm going to do the inside of the house first. Square root of 81 is 9, but it's still inside of a house. So that turns into 3. Again, we're doing principal roots here. Now, I have a subtraction problem inside a grouping symbol, so I have to do that first. Then I take the square root of 16, I get 4. Now I have two grouping symbols with the addition outside, so I've got to do them first. 6 plus 11 equals 17. Okay, now we're going to, just like we did with the exponents, we're going to cover a lot of ground. So we're going to multiply. If you multiply two roots, what you can do, well, we're not even doing it. What are they doing here? Okay. Yes. The fastest way to simplify a root is if you know that there's a perfect square that's made up of that number. So here's what I mean. This is how this textbook will always do it. What they're saying is the square root of 300, you know what? I think it would even be better like this. Isn't this number that I've created inside the house the same thing as 300? It is. And one of the numbers inside of there is a perfect square root. It's a perfect square. So the square root of 100 is 10. So you could turn this 100 into the 10. Like I just do the square root of this part. And the reason they're saying this is possible is because you can split them up or multiply them back together. So this would be the 10, the square root of 3. Yeah, now I'm going to show this to you here. I won't show you this all the time, but if you didn't know the perfect square, what you can do is you can break that number all the way down into the primes. So again, this is a more advanced class on this, so I won't spend a lot of time. But again, I have all of this stuff done if you want older videos. So I've broken all of this down into its prime factorization. And so I should do it like this. So I've broken 300 down into its primes. So all of this here that I've written really is the number 300. Now if you're doing a square root, that's like a little 2 is here. We're in the world of 2. And it takes pairs to bring a number outside of the house. So every pair of something can bring out a number. So I could bring out a 2 for this group and a 5 for this group. Well, if you bring out two numbers, multiply them back together, and that's how we get the 10. So if you know this perfect square, this is the approach the book uses. And it's pretty mathematical. So if you know that, like you're good at the roots, then this is the fast way to go. But if you don't know one, and this happens to me all the time, I don't see one, I will break it down into its primes and keep the principle in mind. A pair of 2's lets me bring out, a pair of 5's lets me bring one out. Multiply those together, I get 10. Okay, so let's look at this one. So oh yeah, they just split it up. Okay, do I like how they're doing it? Well, let me explain their way, and then I'll talk you through mine. So they split up this original problem. They saw 162 must be 81 times 2. And they've split it like this because they saw 81's a perfect square. And then look, they have a to the fourth and b to the fourth. Well, the square root of a to the fourth would be a to the second. So it's a perfect square, and so is b to the fourth. So they grouped together the perfect squares. Now the perfect squares are going to create this. Everything left over gets you that. Now the way, if you want to see it the other way, you could break 81 down all the way into its primes. I'm not going to do that again, but I'm going to show you if I had 5 a's under there and 4 b's, I could do the same trick. I can match up a pair of a's and a pair of a's. So every circle lets me bring one out. So I could bring out a single a and another a, which is where the a squared comes from. I could bring out a b for this circle and a b for that circle, and that's where that one comes from. There'd be an a left inside. Now if you broke down 81, you could do this again with the number thing. I'm not going to do that again, but what's going to come out there is a 9, and you'd have a 2 left behind. So if you're really good at math, then you see the perfect square idea. But if not, you could always break them down long ways. And if you want some more on that, again, I've got some Algebra 1 videos on that. Okay, so if I'm going to do the perfect square approach here, here's what I've got. So those 2's and z's make things a little... Here's what I did. I put everything that had a square root over on the left, and everything else I kept over on the right. So again, you could do this long ways. Again, check out my videos if you want to see the long way. But these all have square roots. So 5xy, and what's left in the house does not have a square root, 2yz. So what's left in the house couldn't come out because it didn't have the square root. Okay, some more review here. If you're multiplying two square roots, you can multiply together what's inside of the house. The 12 and 3 can multiply. Now this one has a square root, so we can take that square root and be a 6. We can do it here even with x's. I can multiply what's inside of there. I'll multiply the numbers and multiply the x's. Now this is a perfect square. So 100 has a square root, and x to the second has a square root. So that would be my answer. Now, you can break a square root underneath if you have a fraction underneath a square root, it works the same that you could make it the square root of the top over the square root of the bottom. You can always go, it's a useful trick we might see in this course, you can always go back and forth between these, whichever is more convenient. If you want it to be a fraction under there, fine. If you want to split it up into two individual roots, that's okay too. So whatever is to your advantage. So why would I want to do this? I'm going to split this into 2, and the reason why that would be helpful is because the bottom has a square root that I'm comfortable with, which would be 6. Now the top didn't, but having the bottom have one was helpful. So I can do that trick again. I would check to see if there's anything that could simplify right here that might make it helpful to leave it as a fraction and then split it up, but nothing simplifies. So I'm going to turn this into 2x squared over 9y to the fourth. Now on the bottom, I've got perfect squares. That's 3y to the second. On the top, the x to the second is a perfect square, so I could bring out an x, but that 2 can't come out. Okay, now here's where we would find it useful to go the other direction. So what I mean is we're going to put them back under one root. And the reason I might want to do that is because this fraction then simplifies. We can follow our exponent rules from before, simplify this down, and we would get down to this. And that's helpful because that's a perfect square and would leave us with 3x squared. So I'm going to do that trick again. Now this can tidy up. If this was just a fraction and there was no root there, I could divide 9 by 3. So I've got a to the fifth. I could take away 4a's from the bottom. 5 minus 4 would be 1a. And then I have 14 b's on the top. Take away 5 of them, I would have 9. Okay, but now it was underneath the root, so we got to leave that. Okay, now do we have any perfect squares? Well, the only thing that'll come out, I wouldn't normally write it like this, but I could bring out the 8. So I could bring out 8. So I have b to the 8th, which is a perfect square. I didn't say that very well. And then everything else does not have a perfect square. So if I had 8 b's, I could bring out 4 of them, but 3ab is going to have to stay inside. Now, adding roots works the same as variables. If this was 5x plus 2x, they're the same thing and I can combine like terms. If these were the same kind of root, I could combine them. Now the problem here is that right now they're not, so it looks like, why did they do this? Well, if we simplify the 5 to the 12th, there's a root in there. So here they're showing it to us. There was a perfect square inside of there. 12 is 4 times 3, so I could bring out a 2 and make this 10 to the third. So now, if you simplify this guy, just using the rules of roots, it turns into this. Well, now we've got 10 to the third plus 2 to the third square root of 3, 10 to the square root of 3 plus 2 to the square root of 3. Those are the same kind of thing. The root works like a variable, and they're the same variable, so I can add that up. I've got 12 square roots of 3. So if that was unclear to you, first simplify this. If I had the square root of 20, again, I'm doing the perfect square method, but 20 is made up of 4 and 5. Well, 4 has a square root, it's 2. Now I already had a 6 out of there, so if the 2 comes to join it, it's going to make it 12 square root of 5. Okay, now these are like common terms. These are this, I can combine these. And it's like there's a 1 out in front of there. I have one of them over there, 12 there. I have 13 square roots of 5. Okay, now this one is really complicated, and there is some oh no, we're going to have to simplify first. I thought if all of this was a direct match right now, we could just combine them and say 20 minus 14. But it's not a direct match quite yet. So let's bring out any perfect squares. Wow, that's complicated. What are they doing here? Yeah, well, forget that. Let me show you. So let's break down 72. 72 would be 2 times 36. So I have this. So I've separated these into the ones that are perfect squares and the ones that aren't. So I've got a 6a b to the second that can come out. Now when the 6 comes out, there's already a 20 there. So I'm going to multiply those together. Get 120. Again, a to the second, take square root of that, you can bring out an a. B to the fourth square rooted, you bring out 2 b's. And the 2ac can't come out. Now let's do the other one. So 8 is 4 put the 2 over here. That makes 8. I've got a to the second. So I'm separating the perfect squares from those that aren't. Again, this is not the method I typically teach at college. I usually show people, if they're struggling, I show them the longer way. But if you're good at this and understanding this, this is much faster. Okay, so I separated the perfect squares, and I can bring out 2ab to the second. Oh, but I had a 14 out there. So I had a 14 out there. So let's bring this together. So it's really like a negative 14. So I had negative 28, ab to the second, 2ac. Now, what's interesting here, all of this is the name. Every single part of that. So they have to match identically. This is like the word. It's the entire name of a team. That entire name has to be an identical match or we can't combine them. And although it's extremely complicated, all of this is exactly the same. So I can put them together. So if I did that right, we'd have 92 ab to the second square root of 2ac. That's pretty hard. Okay, I thought we were going to work another one, but we're out of examples there. So really fast through some of the properties of roots and how to combine them. This one's important. This is definitely prerequisite information, so please make sure you have this. And as always, if you want to see some older videos where this goes slower, we've got those too for Algebra 1.